Okay, the final section for chapter 2 is 2.5 perpendicular lines. There is another section 2.6, however, we've already kind of incorporated it. We will go over that finally in the review session. I'll go over a few of those theorems, but for now we're just going to focus on 2.5. So 2.5 is about perpendicular lines, and we're going to apply the definition, the theorems about perpendicular lines. So most of you probably have an idea in your head when I say something is perpendicular, or we're talking about two perpendicular lines, you already know what that looks like. So how do you define it? Well, perpendicular lines are two lines that intersect to form right angles. Well, what are right angles? Right angles are angles that are 90 degrees. So if you were going to sketch a picture of two lines that are intersecting to form a right angle, we'll go ahead and do that. So over here, if I sketch a picture, here's my two lines, and they look like they are perpendicular to each other. Now, how do you know they're perpendicular? Well, there's one symbol that we'll use, one notation, and it's this little box. It looks like a square we put in the corner where the intersection of the two lines takes place. So that red square that I put there, that red symbol, indicates that yes, in fact, those two lines are perpendicular to each other. So that indicates that this is a 90-degree angle right here. So question A says, what do you know about the other three angles formed by the two intersecting lines if one angle forms the right angle? How do you know this? So notice we have four angles here, 1, 2, 3, and 4. So the first angle I told you, well, that I put the symbol in here, that's 90 degrees. How do we know that the second angle or the third angle, the fourth angle, how can we find those measures? Well, some of you might recall that here, this is a straight line. And if two angles form a straight line, that means they must equal 180 degrees. Remember, that was the angle addition postulate that says if two angles form a straight line, they have an adjacent side with a common vertex, then when we take the sum of them, it's going to equal 180 degrees. Well, if these two are going to equal 180 degrees, that means my missing angle here is 90 degrees. Now, the other reason that we know 1 and 3, or that 3 is a 90-degree angle, is you might say to yourself, oh, right, we just did this on the quiz, or we just studied this, and this is vertical angles, right? Vertical angles are congruent. And here, these two angles right here are vertical. So if angle 1 is 90 degrees, then angle 3 must also be 90 degrees. And so that, or you could have said angle addition postulate with this line. And now that we know this is 90 degrees, this is 90 degrees, we can say angle addition postulate between 1 and 4, so this is 90 degrees. Or now that we know 2 is 90 degrees, we can go with the vertical angle theorem, right? So we have vertical angle theorem, and we have angle addition postulate, which tells us that all around the two intersecting lines that intersect at 90 degrees or that are perpendicular to each other, we know they're all 90 degrees. So how do we know this? Because of angle addition postulate or because of the vertical angle theorem? The symbol that means perpendicular is this symbol here. That means if I put line L as perpendicular to line M, that means when I drew them, I could sketch line L, sketch line M, and then put the symbol in the corner, which shows that I comprehend what this means. Line L, perpendicular to line M. How do we know that? Because of the symbol in the corner. So this is the symbol on the diagram. This is the symbol we would use in sentence, right? This is the notation we would use to explain what we were talking about visually. Okay, look around the room. Can you give me 3 real-world examples where perpendicular lines exist? So looking around the classroom, you should see many, right? Where the wall meets the ceiling, where the floor meets a wall. Look at the corners of the windows, the doors, the posters, your textbook, pieces of paper everywhere, the cardboard box, recycle box in the corner. All of those things have corners that are 90 degrees. So if you call the top of the poster, right, and the bottom of the or side of the poster, this is a 90-degree angle. So there's many real-world examples of perpendicular lines. Okay, let's look at this next example. if AB, line AB, is perpendicular to line CD, so I'm going to go ahead and put the symbol here because that will help me. Use the diagram to classify each statement as true or false. So go ahead and push pause, try to go through these on your own, and then check your work with me as soon as you're done. So now check your answers. You should have gotten false for the first one. So we know that AB is perpendicular to CD, so maybe you want to put that symbol in every single corner to help, right, with each problem. So they don't look perpendicular, that's the thing you need to get used to, right, is these two lines don't look perpendicular. Maybe I'll highlight them like this, but they are, if I'm telling you they're perpendicular, then they're perpendicular. And what do we know about perpendicular lines? That they form 90-degree angles, 4 congruent 90-degree angles. That's the definition up here. Right? It says 2 lines that intersect to form right angles, or we know what a right angle is, that's 90 degrees. So they form right angles, and there's 4 of them. Oops, okay. So is AB perpendicular to EF? Well, no, because EF is not the same line as CD, therefore that's false. Is angle CGB a right angle? Yes, it is, because that's the 2 lines that intersect to form right angles. CGA, yes, it is. Is the measure of DGB 90 degrees? Yes, because that's the 2 lines that are intersecting to form these 4 right triangles. And right triangle means 90 degrees. Are EGC and EGA complements? Yes, because they are sharing the same side, and these 2 angles added together create the overall big angle AGC, which is 90 degrees. So yes, these 2 angles are complements of each other. Is DGF, so DGF, complementary to DGA? Well, no, DGA in itself is 90 degrees, so these 2 add up to more than 90 degrees, therefore they are not complementary. And finally, is EGA complementary to DGF? Well, yes. Why? Because these 2 angles are vertical angles right here, right? These 2 angles right here are vertical angles. And we know vertical angles are congruent. Therefore, if these 2 angles, CGE and EGA, were complementary, then DGF and EGA are also complementary, because CGE and DGF are vertical angles and they're congruent. And if we were doing a proof there, we would do substitution property. We would substitute angle DGF in for CGE to say that yes, they are also complementary, right? So we could substitute this one in for here. All right, let's do another proof. The definition of perpendicular lines is closely related to the following theorems. If 2 lines are, then they form congruent adjacent angles. Congruent adjacent angles. Okay, adjacent means that they share a side. Congruent means they're all the same measure. So we are going to try to prove this theorem. And if we prove it, that means yes, in fact, it is a theorem. Well, we already know it's a theorem, so now we're just going to prove that it is true. Remember, the hypothesis is your conditional. The conditional is the given portion, and the conclusion of the conditional is your proof portion. So if I give you line L is perpendicular to line N, well, that was given. Now, why are angle 1, angle 2, angle 3, and angle 4 90-degree angles? Well, I would say that's the definition of what? Right here. They form right angles, and they're 90-degree angles. So it's the definition of perpendicular lines. So the definition of perpendicular lines is that when 2 lines intersect, they form 4 right angles. So these 4 are right angles, which means they're 4 90-degree angles. So then why are angle 1, angle 2, angle 3, and angle 4 congruent angles? That's just the definition of congruence. right? If they all equal to each other, then they all must be congruent. So if angle 1, the measure of angle 1 equals the measure of angle 2, then we also know angle 1 is congruent to angle 2. These are the same. So it's just definition of congruence. Okay, moving on. If two lines form congruent adjacent angles, then they are perpendicular. So now we're going to prove this theorem. Alright, so if two lines form congruent adjacent angles, then they are perpendicular. So go ahead and maybe just pause here for a minute and try to fill this out. So pause here for a minute and try to fill out this proof and see how you do. Okay, so how'd you do? We have given angle 1 is congruent to angle 2. Well, we know if they're congruent to each other, they're also equal to each other. So that was given. Measure of angle 1 plus measure of angle 2 equals 180 degrees. Why do we know that? Well, it's given over here in the diagram with measure with angle 1 and angle 2. And if they form a straight line and they share a common side and they're side by side, that's because of the angle addition postulate. The measure of angle 1 plus the measure of angle 2 equals 180 degrees because of the angle addition postulate. Now what do? If we know this is true, we can take the measure of angle 2 and substitute it in for the measure of angle 1. So we did substitution here. So this is a substitution property. If we have the same thing added to each other, that's the same as just simplifying it. Twice the measure of angle 2 equals 180. So therefore, how do we get from twice the measure of angle 2 equals 180 to just the measure of angle 2 equals 90? Well, we divided each side by 2, so that's why we have the division property. And then, if the measure of angle 2 equals 90 degrees, well, that goes back to our definition of perpendicular lines, and those two lines must be perpendicular because two lines that intersect to form a 90-degree angle, that means they are perpendicular. So there you have it. Now, what do you notice about the relationship between Theorem 2.4 and Theorem 2.5? Theorem 2.4, look at it. It says, if two lines are perpendicular, then they form congruent adjacent angles. If they are perpendicular, then they form congruent adjacent angles. This says, if they form congruent adjacent angles, then they are perpendicular. So they are each other's what? They are the converse of one another, right? We just switched the hypothesis and the conclusion, so they are each other's converse. They are the converse of each other. And finally, our last theorem in this section, if the exterior sides of two adjacent acute angles are perpendicular, then the angles are complementary. So right here, if the exterior sides, so here's an adjacent angle, AOB and BOC. And if the exterior sides of two adjacent angles are perpendicular, so if AO is perpendicular to OC, because they're adjacent angles and these are the exterior sides, then these two angles, AOB and BOC, must be complementary. So when you look at the diagram, hopefully that becomes obvious. But now we have to prove that this is in fact true. So what's the given? The given is that we have the exterior sides are perpendicular. So OA is exterior, OC is exterior, so these rays are perpendicular to each other. So that's given. How do we then know that the measure of AOC is 90 degrees? Well, that's the definition of perpendicular lines, right? If two lines intersect to form 90 degrees, then that means their angle is, two lines intersect that are perpendicular, then that means their angle formed is 90 degrees. The measure of angle AOB plus BOC equals AOC. That, I hope you have seen enough that you see that's the angle addition postulate. AOB plus BOC equals AOC. Angle addition postulate. Now, what do you think we're going to substitute in here? Well, the only thing we can substitute in has to be relative to these two lines. So this has an AOC, this has an AOC and a 90, so we're probably going to put 90 in for AOC. So now we say that these two angles add up to 90 degrees. because of substitution property. And therefore, if these two angles add up to 90 degrees, what does that mean about